Hi everyone. So we're doing an experiment today for a mechatronics system that essentially simulates how a control system would work if for a car temperature sensor. And what do I mean by that is, let's say this case where your outside temperature is about 57 degrees Fahrenheit right now, and then you're setting your temperature to be 75. So what the system is doing, it's compensating for the outside temperature and trying to meet and bring the inside cabin temperature to 75. Now we can essentially do this control system using a closed loop control. And to demonstrate this, I'm going to show you a heating system. So this is a temperature control lab heating system that has two heaters, and it has two temperature sensors. They both feed the data to the analog signal, which measures the temperature, and then we use a MATLAB simulation to demonstrate this. So what you have here is we're reading analog pin 0 to get the temperature. We're treating it as the outside temperature, the one you are seeing, for example, 57 degrees. And then we get the cabin temperature from analog pin 2, and that gives us the temperature reading for the cabin. And we're controlling the temperature, so we have to simulate that we fluctuate day and night temperature shift here. And we use the sine wave. We set the amplitude to 20 and the bias to 20. So that takes your temperature from 0 to 40 degrees Celsius. Everything here is degrees Celsius in a cycle of 600 seconds. And we reason why 0 to 40, so 0 is not the temperature you will experience, is because 0 here basically tells the heater to switch off. So this is your basically when it's off, you see it's a darker black, and when it's on, you'll see the to be pinkish. And the cabin temperature, the way I had set 75 in the car, here is set at 30 degrees Celsius. And a PID controller basically controls what you really have versus what you set. So you set 30, and then you subtract that here from the temperature that you're monitoring, and we send it to PID controller. Proportional is set to 10, the integral set to 0.5. So proportional really bumps up, gets us to the 30 very quickly. The integral compensates for the error over time, and so we want it to be as close to 30 as possible. And then the derivative is set to 0. So it really and then we bring an outside fluctuation here using a feed forward. So the outside temperature goes through a negative 0.5 feed forward, which gets subtracted here. And so let's say if the difference between cabin and outside is like 5 degrees, so 5 times 5, 25, that's 2.5 degrees Celsius difference that would go into our system. And then we measure, we switch on and off the heater based on that behavior, and that's how we bring the temperature to as close to 30. So I've been running this for a while. Right now it's been running for 363 seconds, so we can monitor this. So the way I'm monitoring this is I get the temperature 1 from outside temperature feeding into this mux, and then the cabin temperature. And we'll see from the scope, that's what we have right now. So you see it's cold outside today. We're doing this experiment in the garage, and the temperature goes up. The sine behavior is what we want to observe because of the outside temperature fluctuation, and you should see it go up quite high. And then the blue one here is your cabin temperature maintained at 30 degrees. So you can add a Kalman filter or other types of filters, or even like moving average smoothing to smooth some of this noise. But this is really good, keeping it at 30 generally. And then even if the outside temperature goes up or down. And so eventually it'll start to look something like this. This is kind of a full simulation and ran for 1800 seconds. So you see how it's well maintained at 30, the outside in orange, the outside in blue and the cabin temperature in orange. And yeah, that's what we have today. Thank you. Thanks for watching.